Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last 3 lectures, we looked at Thevenin and Norton equivalent circuits looking into the terminals of the small signal model of the bipolar junction transistor in terms of the Thevenin equivalent seen looking out of the other terminals. These lectures were fairly abstract and complicated, and based on my YouTube channel analytics, weren't terribly popular either. Although admittedly a title like emitter-Thevenin equivalent circuit is not exactly the most eye-catching combination of words ever put together. In any case, all of that hard work is now going to pay off when we analyze some amplifiers, and we'll start with the ubiquitous common emitter amplifier. So the kind of amplifier I'm going to explore here uses a fixed bias scheme. This is fairly common, and basically I'm considering the amplifier itself to be this part of the schematic here between and including these capacitors. The job of these capacitors is to basically act as DC blocks, so we can have some internal bias voltages that differ than what is being used by the outside world. RS here represents whatever the output impedance of our voltage source that is driving the circuit is, and RL represents some kind of external load. Now, don't think about this as a load in the sense that you might when thinking about power transfer calculations. We're not trying to maximize power to do work or something like that. This load really represents the input impedance of whatever this amplifier is feeding. And it's not really necessary. We could do all of the analysis without this, but it's just as easy to include it here, so we go ahead and do that. Now, one thing that can be a little complicated is what I've called RC here is sometimes called RL, and it's called a load resistor. And I find that to be very confusing because when people use that kind of terminology, they don't mean an external node like this. They mean something that's fundamental to the operation of the circuit. So to avoid that confusion, I like to just call it RC for a collector resistor. With the fixed bias scheme, we choose a couple of resistors, and that forms a voltage divider. And then down here at the emitter, if R3 here is a short circuit, so if R3 is 0, then we say that the emitter is fully bypassed. If we actually have some resistance R3, we say that the emitter is partially bypassed. I'll talk a little bit more later about alternative configurations for capacitors and resistors at the emitter. We can imagine decomposing this into 2 circuits. One is the DC bias circuit, and the other is the small signal circuit, and you'll also hear people use the term AC circuit. So here I'm indicating AC or DC inside of the BJTs to indicate that only this transistor over here is really the full BJT. These other transistors are representing subsets of the essence of a BJT. In later slides, I'm not going to include these notations. I'll assume you'll figure out what I mean by the particular context. So for the DC bias circuit, we open up all of the capacitors. For the small signal circuit, for now we're going to assume that the capacitors act as shorts. Later in the class, we'll talk about ways of treating these capacitors more carefully and considering their effect on the frequency response of the circuit. But for right now, we'll just treat them as shorts. In a previous lecture, we showed that we could compute the bias current IC using this formula here, where we plugged in various expressions for Thevenin equivalent circuits seen looking out of the base and the emitter. So I would suggest checking out that lecture if you haven't already. In any case, let's assume that you've done this and you know what IC is. Now, it's also good hygiene to make sure that your circuit is actually acting in the active mode. And for that, we can have this strategy where we also compute a Thevenin equivalent circuit looking out of the collector. And then we can substitute these expressions into this expression for the voltage between the collector and the base and make sure that that's positive. Again, that's something that we looked at in a previous lecture. So let's assume you've figured out IC. Let's assume that you've checked to make sure everything's working in the active mode. Then you can proceed with a small signal analysis. So you plug IC into here and into here to compute the raw output impedance of the transistor and to compute the raw transconductance of the transistor. And then using your alpha and beta relationships, you can also figure out what R pi, the raw input impedance of the transistor looking into the base, is when you use the pi model. And then you can also figure out what the emitter resistance associated with the T model is. Anyway, let's assume that you've computed all of these numbers. Now, to use the fancy Norton equivalent circuit looking into the collector that we derived in a previous lecture, we need to figure out what the Thevenin equivalents are looking out of the base and looking out of the emitter. And we'll express those equivalents as VTB and RTB for the base and VTE and RTE for the emitter. So, the equivalent looking out of the base is basically a voltage divider. So R1 and R2 here are just a parallel combination of resistors, and that winds up going on top. And then you get a sum of that with RS, the source impedance. So we have VTB equals VS times this voltage divider. Now, to compute the Thevenin equivalent looking out of the base, I need to zero out this independent voltage source here, and now I have three resistors in parallel to ground, RS, R1, and R2. Okay, so what about the emitter? Well, in this particular case, the Thevenin equivalent voltage looking out of the emitter is just zero. There's no voltage source down here. And the resistance looking out is just RE in parallel with R3. So keep these quantities in mind going forward. I would like to begin our analysis by computing the gain of the amplifier. So I want to know what is VO as a function of VS. So I'm actually going to compute this three different ways. The first way I'm going to compute this focuses on what's happening at the collector. I think this is the most natural solution for this particular circuit, but I will also look at two others. So what we're going to do is we're going to take all of the stuff down here, the BJT, small signal model, and the various Thevenin equivalents, and replace it with this Norton equivalent circuit looking down into the collector that we computed last time. So the only thing we have left from the original circuit is this RC and this RL. We computed what this short circuit current is and what this RIC is in a previous lecture, and I will repeat those formulas a little bit later. Anyway, if I want to know what the output voltage here is, well, I have a current that's flowing here, this ICSC, and then I can imagine that that current is flowing down a parallel combination of resistors to ground. So I have RC and RL in parallel with this internal resistance RIC associated with the small signal model. And I'm going to put a minus sign here because the arrow indicates that we're pulling current out of the node, so that's going to lower the voltage. All right, so that's a start as to figuring out what VO is. Well, what is this short circuit current? Well, from the previous lecture, this is going to be a big GM times VTB minus VTE, except here VTE is 0, so we can just write GM times VTB. In a later slide, I'll give an expression, actually several expressions for capital GM. So what is VTB? Well, we found that on a previous slide. It's just our source voltage seen through this voltage divider at the input. All right, so now I have a series of expressions that end with VO and start with VS, and I can just pile them together and write this mess here. And this looks like a lot, and it is. But we'll see later if you make certain assumptions about certain quantities, this will simplify to some more familiar forms. The point is, if you want to have all the complications in here, you can. So to formally write the gain, let me divide both sides of the expression here by VS. And I'll say that the voltage gain AV is VO over VS, and it's given by this algebraic expression here. All right, so we could stop there as far as talking about this particular solution goes. I would like to show another way of visualizing this computation, and that's called a Mason flow graph. So the idea here is we'll draw a series of points that indicate various circuit variables, starting from where we start and ending with where we want to end up. And we have some intermediate variables in between. And then for each of the arrows, we're going to draw the constant we need to multiply by in order to get the next element of the chain. So this isn't really necessary for what we're doing right now, but this Mason flow graph idea comes in very handy when analyzing feedback amplifiers and you wind up with loops in the graph. So I like to introduce them now just to start getting you used to looking at them. So what is this capital GM and this little RIC? Well, in the previous 3 lectures, we computed 5 different formulas for GM, and you could use whichever one you want, depending on which one you think is best in any given circumstance. And we had 2 different formulas for RIC. And this RIC formula involved this RIE, and I put 2 possible formulas for RIE down here. Now, this looks like a big mess, and it is, but these are just numbers. And you compute the numbers by putting them into your calculator, or in my case, I'll often write a little MATLAB script so I can change one of the numbers and sort of see how it changes the results. Your mileage may vary. But remember, we're not doing any fancy calculus or differential equations at this point. It's just algebra. So what about the output impedance of the common emitter configuration? I'm going to compute the resistance seen looking into this junction of the collector of the BJT and this collector resistor. Notice that I'm not including the external load here. I'm trying to isolate the effect of the amplifier itself. What we'll do is we'll take all of this stuff down here and we'll replace it with that Norton equivalent circuit. Since we're computing an equivalent resistance, we'll take the independent voltage source here and zero it out. And remember, this current source here is basically that voltage times big GM. So if we zero this out, we also zero out this, which involves basically opening it up entirely. So I wind up with my output impedance, let me call that R out, being equal to RC in parallel with RIC. Remember, for this output impedance calculation, we're leaving out RL. Remember that RIC has 2 different forms. Here's one of them. You can look up the other form in an earlier slide. It's a big mess, but it's nothing that you can't do with a calculator. Notice that this expression has RTB and RTE in it. So let's recall what those are. RTB was this parallel combination of the resistors at the input, and RTE was that parallel combination of resistors at the emitter. Remember this RS, though, that was considered to be the output impedance of whatever source is driving the amplifier. That wasn't really considered to be part of the amplifier itself. So this is a point that I don't think is widely appreciated. The output impedance of a common collector amplifier can depend on the output impedance of the source that's driving it. And that can complicate your thinking a bit. That's not an issue with something like a common source amplifier if you're using a FET, either a JFET or a MOSFET, since we assume that there's no current flowing through the gate. All right, so what about the input impedance? We'll compute the resistance seen looking into the base of the BJT along with the biasing resistors. Notice that I'm not including RS because that's considered part of the source that's driving the amplifier and not the amplifier itself. So what we're going to do here is we're going to take all of this stuff on the right and replace it with our Thevenin equivalent circuit seen looking into the base. Now, in general, that Thevenin equivalent circuit will have a voltage source here, but because we don't actually have any voltage sitting out on the emitter side, we don't over here either. So we just have this resistance RIB seen looking into the base. So our input impedance, which I'll call Rn, is just three resistors in parallel. I have R1 and R2 in parallel with Rib, and if you recall from a couple of lectures ago, Rib is equal to R pi, which is that raw input impedance of the BJT, plus 1 plus beta times RTE, which is this parallel combination out here on the emitter. So remember, we want circuits that have voltage inputs to have high input impedances. So R pi by itself might not be very big, but whatever the resistance seen on the other side of the emitter is, that gets magnified by this 1 plus beta term. So that helps our input impedance. Now, one other important thing to point out is notice that none of the stuff on the collector side shows up in this formula. So fortunately, although the output impedance does depend on what's happening out here at the input impedance doesn't depend on what's happening at the output, which helps your mind be at peace when analyzing these circuits. When we computed the gain, we focused on what was happening with the collector current. That's the most natural solution, I think, to computing the gain, but it's not the only solution. Let's look at another way to compute the gain. We'll start with the same expression, which is that the output is equal to minus the short circuit current times this parallel combination of resistances. Now, if we knew the base current, we could figure out what the short circuit collector current is by just multiplying it by beta. And remember, this is part of our R0 approximation. Now, to figure out what IB is, let's focus on the base. Let's use the Thevenin equivalent seen looking into the base, like we did when computing the input resistance. Again, there would normally be a voltage here in general, but we don't have a voltage out here on the emitter side, so we don't have one here either. Okay, well, IB is just calculated with Ohm's law as VTB over this series combination of RTB plus RIB. And what's VTB? Well, that's the same voltage divider formula that we used previously. So I have a series of expressions that can start with Vs and end with V0, and I compile those together and write an expression like this relating them. And that looks like a big mess, and it is. But remember, these are just numbers, and you can plug the numbers into your calculator. So let me compute the voltage gain by dividing both sides of the equation by Vs. And that tells me that A sub V, the voltage gain, is this multiplication of factors. And once again, I would like to draw this in terms of a flow graph. So we'll let the variables here be Vs, VTB, IB, the short circuit current, and V0. And then we have our voltage divider to go from Vs to VTB, our Thevenin equivalent voltage at the base. And then we'll multiply by this 1 over resistance sum term in order to get the base current. And then we just multiply by beta in order to get the short circuit collector current. And then we multiply by this parallel combination of resistors, being sure to include this minus sign in order to actually get the voltage at the output. So that Mason flow graph is just another way of trying to organize this computation in your head. Now, maybe that's not enough for you. Maybe you're sitting there thinking to yourself, I want yet another way to compute the gain of the common emitter amplifier. Well, I have one for you. Let's focus on the emitter. Starting from the same place, VO equals minus short circuit current times this bunch of resistances in parallel. Except this time I can say, oh, the short circuit collector current can be written as alpha times the emitter current. Again, there's some business going on here involving the R0 approximation, which lets us avoid thinking about primes, yada yada. Since I'm thinking about the emitter current, let's use our Thevenin equivalent circuit for looking up into the emitter. Here I do have a voltage on the other side, and it manifests itself as VTB. And now I can compute IE as just being VTB over this series combination of resistances according to Ohm's law. And what's VTB? Well, you've seen this formula several times already. And now, once again, I have a series of expressions that start with Vs and wind up with V0. And I compile those together and write this expression for V naught in terms of Vs. And let's divide both sides of the expression by Vs in order to write AV equals VO over Vs equals a whole bunch of stuff. Here, our Mason flow graph formula is very similar to the one for the base focus solution I showed you. We basically just have IE here instead of IB. So the first transition is the same, just this voltage divider. And then the transition to the emitter current is like what we had before, but instead of RIB and RTB, we now have RIE and RTE. Instead of beta, we have alpha. And then the last transition is the same. So the formulas we've created are a bit of a handful. Let's consider some simplified special cases. All right, so let's start by supposing that the source resistance is 0, the load resistance is infinite. So basically we take those out of the circuit, and R naught is infinite. So we're going to use the R naught approximation on everything. In that case, this parallel combination reduces to just RC, and if RS equals 0, this divider in front turns into 1, so this simplifies to GMRC. Now remember RTB, the Thevenin equivalent looking out of the base? That's the parallel combination of R1 and R2 with RS all in parallel. So if RS equals 0, this term goes away entirely, and we can write GM like this. Now let's also suppose that beta is big, because if beta is big, then alpha is pretty close to 1, and we can approximate big GM like this. And let's multiply the numerator and the denominator by GM in order to write it like this. All right, so let's take this expression for GM and plug it in here. Then we can write AV as approximately minus GM over 1 plus GM RTE times RC. And now I would like to consider two separate cases. In the fully bypassed case, RTE is equal to 0. So our voltage gain is the raw transconductance gain of the transistor times the collector resistance. Now this is problematic because this transconductance gain can vary all over the place in practice. So you generally only see something like this used if there's some other feedback mechanism somewhere keeping things under control. Now let's consider the case where we're not fully bypassed. So if we have the situation where this GM times RTE term is a lot bigger than 1, then we can effectively get rid of the 1 and cancel out the GM. So then we have minus the collector resistance over the combined resistance at the emitter. And this is the formula you're probably used to seeing on most websites or whatever. I just want to make the point that this doesn't drop out of nowhere. There's a lot of approximations that you make in order to cause this formula to appear. Now, it looks like we did a lot of really complicated things, but essentially the answers popped out from a series of small individual steps. If you take a more standard approach where you take the small signal model and substitute it in and then derive all of the input and output impedances and the gains using that small signal model from scratch each time, this is actually a lot more complicated. Using these Thevenin and Norton equivalents looking into the terminals allowed us to basically write down answers essentially by inspection. Before we close out, I wanted to talk about an alternate scheme of arranging these resistors and capacitors, as I earlier promised. So with the scheme that's been presented here, the DC calculations involve computing a Thevenin equivalent looking out of the emitter that gives a resistance REE of just this resistor RE, whereas the small signal Thevenin equivalent seen looking out of the emitter was RE in parallel with R3. So there's an alternate scheme that you could use, and I think this one is probably more common, and I think definitely you would see it in more textbooks. And here we have RE in parallel with the capacitor, and then we have R3 in series with that. Now the scheme on the left is a little more convenient for playing around with trim pots on the breadboard, because what you can do is you can make RE a pot, or more likely a resistor in series with a potentiometer hooked as a variable resistor, and you can adjust that to set the bias. And then after you set the bias, you can adjust the gain by adjusting R3 with another trim pot. On the other hand, in the circuit on the right, R3 sets the gain, but it also plays a role in the bias. So you can't adjust this R3 without also changing the biasing, which I guess also can affect the gain. So it's just a lot more complicated to deal with if you're trying to adjust things. But if you're just fixing a few resistors, good enough. The last thing I wanted to mention is that the vacuum tube equivalent to these common emitter amplifiers are common cathode amplifiers. So you can learn about those in my guitar amplification and effects class.